Hello again. We're going to begin a study of electrical circuits, starting with the simplest of all circuits that I call a simple circuit. A simple circuit is diagrammed here. I show a battery symbol with a positive and negative terminal. I show current coming out of the battery and traveling through some device, anything through which current can flow. It might be a light bulb. We symbolize the battery's strength, so to speak, its electrical pressure, so to speak again, as E, script E. Looks a little bit like the Greek symbol uppercase epsilon. That is what's called the electromotive force of this battery. That phrase is a misnomer, a misnaming, because the quantity we're referring to is not a force. Force is measured in newtons. Instead, the electromotive force, which we can say EMF, is the amount of battery energy given up to electrons for each coulomb worth of charge that leaves the battery and circulates around the circuit. The electromotive force is therefore measured in energy per time, joules per second. I misspoke. I meant to say the electromotive force is measured in units of energy per charge, joules per coulomb, joules per coulomb. Now, joules and coulombs are standard units, and so we could get by with letting the units of electromotive force be joules per coulomb, but instead we have a single word that stands in place of that ratio of units. It's called the volt, abbreviated uppercase V. So 1 volt is equivalent to 1 joule per coulomb. Let's look at a simple example. Suppose the EMF of a battery is 50 volts. That's a number that never changes, no matter what sort of circuit this battery is used in. 50 volts is the electromotive force. That means for every coulomb of charge that's pushed out of the battery, 50 joules of energy is consumed. That energy is taken from the chemical energy stored in the battery at the factory. Suppose the amount of energy stored in a new battery is 30,000 joules. Further, suppose that we wish to calculate how many coulombs of charge can be pushed out of the battery before all of the battery's energy is exhausted. Well, we lose energy at the rate of 50 joules per coulomb. We start with 30,000 joules, and so we do the division to get the following fact, that this battery will be dead after it's pushed 600 coulombs of charge out of it. Now we'll come back to the 600 coulomb value in the next example, but not until I've discussed the meaning of I. I is a so-called electrical current. We can just say current. It can be calculated by dividing the known number, if you know it, of coulombs, the known amount of charge Q that leaves the battery, over a particular measured time lasting T seconds. The units of electrical current are coulombs per second. We let the word ampere, abbreviated uppercase A, stand for a coulomb per second. So far we've learned 2 new vocabulary terms, electromotive force and current. And the units associated with those quantities are volts for electromotive force, and amperes for electric current. Let's consider a final example before we close this very brief video lecture. Suppose the current out of the battery we're talking about here is 3 amperes. How one would know what the current out of a battery is, we'll discuss in the next lecture. 3 amperes out of the battery. We know that the new battery is capable of releasing to an external circuit 600 coulombs before it's dead. How many seconds then can this battery last doing this job, which is to output 3 amperes of current? Well, we have 600 coulombs. We're using energy at the rate of, we're consuming charge at the rate of 3 coulombs for each passing second. Final result is that after 200 seconds of this battery's operation, it will have become dead. Any questions? Let's move to the second part of our discussion of simple circuits. We'll learn how to determine the current out of a battery.